Now let us try to find the acceleration due to gravity at that height. Which height? The height at which the satellite is revolving. So suppose this is our Earth and this is that orbit, and that satellite is here at a height h here, right? Usual notations: my mass of Earth is m, radius of Earth is r, height is h above Earth's surface, and the radius of orbit, which is small r, and that is equal to r plus h. Mass of satellite is m here, okay, and now my g is what? G is my acceleration due to gravity on Earth's surface, and gh is acceleration due to gravity at height h, and g is acceleration due to gravity on Earth's surface. In the last video we have seen that my g is equal to gm upon r square. That's what we have seen. What about this gh then? Now gh would obviously be equal to gm upon r plus h square, correct? And then if I want to find this, okay, I know this, I know this, I know this, and I know this, but then there is one more way of doing it. If I do 2 upon 1, so that would simply imply that gh upon g is equal to, now this gm and this gm, they are going to get cancelled, both the quantities in the numerator, correct? So my r plus h square is in the denominator and r square is in the, will go in the numerator, correct? So we can simply say that g at height h is equal to g into r upon r plus h whole square, correct? So every time I need not use acceleration, this universal gravitation constant and mass of Earth and do all that calculation. Instead of that, what I can do is, I know this value of g on Earth's surface, I know radius of Earth, I know r, this r and this h, correct? And we can easily find that out, okay? Now, so far I have seen this expression, I have seen this expression, I know my v is equal to root over gm upon r plus h, and this velocity is which velocity? It is critical velocity or then orbital velocity of the satellite. Now again, if satellite is orbiting close to Earth's surface, then, and if my h, if h is fairly small compared to my r, then I would simply write this as gm upon r. So it's like, 6.4 million meters, and if you compare about 500 meters with that, or maybe 1000 meters with that, correct, the difference would be very negligible and it would fairly be equal to this value, because it is going to be this r plus h and r, they are almost going to be equal, and square root of r plus h and square root of r, they are going to be fairly same, okay? So this would be my third important expression here. Now there is something people say, there is something called escape velocity. What is escape velocity? So now for understanding what is the escape velocity of a satellite, we need to understand what is the binding energy. Now when we say binding energy, it is the energy with which it is bound with the Earth. So that means for that we will need to find the total energy of satellite, correct? Now for finding total energy of the satellite, we need to know the kinetic energy and the potential energy, right? So let us see how it is. So my Earth is here and satellite is orbiting like this, and it is here at height h, my radius of Earth is r, mass of Earth is m, and the radius r of the orbit is r plus h, mass of satellite is m. So these are things that we know. So now it is orbiting in a circular orbit, right? So now the velocity would definitely be equal to the critical velocity or the orbital velocity, which is equal to my Vc is equal to root over gm upon r plus h, or small r. So now here, if this is the velocity, then what is the kinetic energy of the satellite is half m Vc square, and would it not be equal to half m into gm over r? Now in place of r plus h, now I am going to take a shortcut. I am going to write small r here. Now, so my kinetic energy is equal to half gmm upon r. Now for getting total energy, we need to know the potential energy. Now here we need to understand what is gravitational potential, because we want to have gravitational potential energy for which gravitational potential would be needed. Now in electric potential, you must be remembering it is electric potential at a point is equal to the amount of work done in bringing a unit positive charge from infinity to that point. Now in case of gravitational potential, the definition would be exactly on similar lines. It will be the amount of work done in bringing a unit mass from infinity to that point. So by that, my gravitational potential it is going to be equal to gm upon r. Correct? It is gm upon r. The gm upon r, and then what about then gravitational potential energy? So I will have to multiply by mass of the body which I want to bring from infinity to that point. Now again here there is one more thing. There is going to be a negative sign here. The reason is it is coming towards the mass, correct? So it is negative over here, and then gravitational potential energy is equal to minus gmm over r. Correct. So this is my kinetic energy relation number 1, potential energy relation number 2, and then if I want to find a total energy, it would be equal to 1 plus 2, and that is going to be equal to gmm upon r plus, so it is minus gmm upon r plus half gmm upon r. Correct. So it comes out to be minus half gmm upon r. Correct. Now, so that is the total energy. Correct. Now you should note here that the total energy has got a negative sign. Now what does negative sign indicate? It indicates that the satellite, it is bound to Earth. It has got negative energy. It doesn't have its own energy. So now if I have to free it from Earth's influence, what do I need to do? I need to supply this much. So that is plus half gmm upon r. If I supply that kind of energy to the satellite, then the total energy will become 0, and then it will be free from Earth's gravitational influence. Correct. So, and then that amount of energy which I am supplying, that is called the binding energy. So binding energy, expression for binding energy would be equal to plus half gmm over r. With this energy, it would be, it is binding with the Earth. Correct. So now, if I need to free it, correct. If I need to free it, what will I do? I'll give the energy in the form of kinetic energy. That is what I can do, right? So then now here I am making it free. So I am making it escape from the Earth's influence. So what kind of energy, kinetic energy I am giving? So my kinetic energy is going to be equal to half m into v escape square. Correct? If I give that kind of energy, then I can escape it. But now here there is one thing. Okay. This expression for binding energy is fine. But then can you give binding in that much energy to some object which is situated at some place on top there? Correct. What I can do is I can see this object is on the surface of Earth and I have full control over this object. I can supply whatever amount of energy I can to this object when it is on Earth. Correct. So now let us have some different expressions for this. Okay, I am going to clear it, and all the notes you are going to get in the description later. Okay, so in the meanwhile I am going to clear this. Obviously now you wouldn't need this diagram. You can simply go back and refer to it. So now let us find the binding energy of a satellite on Earth's surface. So now again we have to do the same exercise. We need to take total energy. Now total energy is equal to kinetic energy plus potential energy. Now obviously if it is on the surface of Earth, it is not moving. So kinetic energy is 0. Plus, now gravitational potential on Earth's surface, it is going to be equal to capital G into capital M upon capital R. Okay, so the potential energy over here on Earth's surface, it is going to be equal to G M M upon R. Correct? Is it positive or negative? It would be positive. Correct. Now what about the energy that we need to supply to this satellite? It is half mv square, but now we want to escape it out of Earth's influence. So the kinetic energy to be given would be equal to half m into ve square, where ve is the escape velocity. Now what I'm going to do is I'm going to equate this with this. Correct. So so my half into m into ve square is equal to g m m upon r. Correct. So this m gets cancelled and my ve square is equal to 2 gm upon r. So my ve is equal to root over 2 gm upon r. Now you must be remembering that my orbital velocity vc, or critical velocity for that matter, it is root over gm upon r for a satellite orbiting very close to Earth's surface. Here if you see, I can say that v escape is equal to root of 2 times v root 2 times vc. Correct? So it is root 2 into root over gm upon r. So that is the expression for escape velocity. Now I am going to tell you one more very simple way of calculating what is the escape velocity of an object from the Earth's surface. Now here you must be remembering that earlier expression, my g, acceleration due to gravity or acceleration of free fall, that was equal to gm upon r square. Right? And what is my critical velocity? My vc is equal to root over gm upon r. Correct? Now I'll try to put it in this form. So I square it and I multiply by r. So my vc is equal to root over g into r. Right? That is my vc. So in the same way, I can do this. I can do the same thing with this. My VE is equal to root over 2gm upon r into, so square it and multiply by r here. So it is root over 2g r. Now we can calculate. We can exactly. I can do that. Now here what I want to do is, instead of taking 9.81, I take 9.8 to make things little simple. It is 2 into 9.8. What is the radius of Earth? Is it not 6,400 kilometers? I'll write it as 6.4 into 10 raised to the power 6 here. Okay. Now I'll simplify it further here. So that would be equal to, I'm going to write it like this, 2 into 98 upon 10. So that would be 2 into 49 upon 10, 64 upon 10 into 10 raised to the power 6. You know what, I'm going to do this even without using a calculator. So now I'll just group these two. I have this, I have this, I have this, and I have this. I'm going to take square roots. Okay, so this is going to be now I'm going to get rid of square root sign. So it will be 2 into 7 into 8 into, it is 10 raised to the power 6 upon 100. So 10 raised to the power 4, and square root of that would be 10 raised to the power 2. Correct? So this is 2 into 7, that is 14. 14 into 8 is 112 into 2. So 112 into 10 raised to the power 2, that is 100. That is equal to 11200 meter per second, and that is nothing but 11.2 kilometer per second. So any object, irrespective of its mass, if I give it this velocity, it will escape out of Earth's gravitational influence, and that is nothing but its escape velocity, right?